Hello, and welcome to Introduction to Hydraulics, Uses and Applications of Hydraulic Circuits, part of the Fluid 2000 course. I'm your instructor and facilitator, Andy Dibbling. I work at Holland College in Summerside, Prince Edward Island. I've been working as an industrial technician for 30 odd years now, and I've worked on many electrical and hydraulic systems in the past in food processing, petrochemical, machining, mining, and manufacturing. Hydraulic systems are used throughout industry wherever we need portable power and power that is precise in its control and speed. Very useful. The objectives for this course are to describe how a hydraulic system functions, also to describe hydraulic pressure and force, describe the principles of flow of fluid in a hydraulic circuit, and describe hydraulic energy, its work, power, and efficiency. So most hydraulic systems are closed systems that contain a fluid within a system of pumps, reservoirs, and conductors. Also, we will have actuators, either linear or rotary actuators, that will provide force either in a straight line, in the case of a linear actuator, or in a rotary motion in terms of a pump or a motor. Now, some of the applications of hydraulics would be in presses, where you need large amounts of power, automated material handling equipment. Many warehouses now are automatically, robotically controlled, and they use hydraulic circuits to move pallets and stack them in the racking. Tubing benders, robotics use hydraulics quite a bit, and actuators to control large valves and drives for conveyors for all kinds of applications. Okay, so we're going to look at the principles of hydraulic force and pressure. We're also going to describe the principles of flow and describe hydraulic energy, work, and power. At the end of this lesson, you should have an understanding of how hydraulic circuits work. In this diagram here, you can see that there is a linear actuator going back and forth. The red indicates a high pressure, the blue a low pressure, and the light green no activity at all. And as you can see that there are two ports, one in the back side of this cylinder, one in the front side of this cylinder. One drives it one way when high pressure fluid is applied, and the other forces it the other way. This actuator down here is electrically operated and is just what we call a spool valve. And it just goes back and forth and shunts the fluid through these different conductors to make the linear actuator indeed work. Pretty standard application for a hydraulic circuit. So before we start, some things you need to know. What is a fluid? Well, fluids take various forms. You're familiar with a fluid as water, hence the name hydraulics from the Greek word for hydro, meaning water, and pneumatics, which is the Greek word for pneuma or air. So if we have a gas system, that's a pneumatic system, and if we have a liquid system, that would be a hydraulic system. Any system that uses a liquid to do some work can be classified as a hydraulic system. The hydraulic systems that we are discussing are industrial hydraulic systems, systems that perform work by making a hydraulic cylinder move linearly or a hydraulic motor to rotate. I find it useful to keep in mind all components, laws, principles, and maintenance techniques we'll discuss are all working to do something very simple, to make something go back and forth or to make something rotate. That's literally it. There's no more magic to it than that. Okay, so what you can expect to see. On the slide coming up, we're going to see a diagram outlining a basic hydraulic system. We'll eventually be outlining in detail how it all works, what everything does, why things work like they do, but for now, we'll just take it for what it is, an absolute introduction. Okay, in this diagram, diagram A, you are seeing a manually controlled spool valve, which will move up and down and will move this cylinder in and out to counteract the load. Now, there are several components in here that are inherent to all hydraulic systems. Let's start down here. First of all, this is the reservoir. The reservoir has several different jobs. One of them, of course, is to hold the fluid. The second, of course, is to provide an area for the fluid to cool down. As the fluid is driven through pumps and through actuators and through spool valves, control valves, and what have you, it builds up heat. Excess energy that isn't used by the hydraulic system to drive a cylinder or to rotate a motor is given off as heat. So heat is the waste product of a hydraulic system. The problem with that is hydraulic oil has a certain viscosity or thickness. The thickness of that oil changes with temperature. It's very important that hydraulic oils, especially in systems like gearboxes, have a specific viscosity or a specific thickness. If they don't, that can lead to damage to the system or decreased performance. So it's very important that the fluid is allowed to cool and settle. The reservoir does this by providing the fluid a place to come into and settle down, drop any contaminants that it may have picked up while going through the system. And here you see a baffle which prevents the inlet strainer from sucking in air or dirt. The pump, of course, is what provides energy to the fluid. It provides flow, but no pressure. The pressure on the inlet is, of course, lower than the pressure on the outlet of the pump. The next thing we have is a pressure relief valve. Pressure relief valve is there very much like a fuse or a circuit breaker in an electrical system. It is designed to limit the amount of force that can be put through the system so as not to damage the components or the process itself. It's very important that this maximum pressure relief valve exists and that it is set up so that it doesn't trigger too often. As you can imagine, if the pump is pumping fluid out of the reservoir and then dumping it right down through the pressure relief valve, there is really no work being done by the system, and all of the energy being consumed by the motor is basically wasted as heat. The next thing we have is a directional control valve. The directional control valve in this top example is a manually operated valve. The operator themselves can crack the valve either wide open or slightly open, depending on how they want the speed of the cylinder to react. This is very useful in systems like excavators and any of your heavy hydraulic excavation equipment. The operator has to have a light touch. The feedback on the controls is quite significant. And if you've ever run a hydraulic control on something like an excavator or a bucket, you can almost feel the dirt itself going into the bucket. It's quite amazing. The flow control valve is next. The flow control valve is a speed control device. By controlling the amount of fluid that flows through this flow control valve, we can control the speed at which the cylinder fills up. It won't affect the pressure, but it will affect the speed. The return line filter makes sure that we have all of the fluid going through the system is going through the filter before it's dumped back into the reservoir to be cooled and lose its air so it can be used again by the pump. Now, in this particular situation down here, you'll notice that there is no flow control valve. The reason is these are electronic proportional valves. These valves are designed to limit flow by how much they are opened. and they have adjustment screws on them, so you can adjust the amount of maximum flow through the cylinder. These valves are a little bit more common now, as you can use a remote control 24 volt DC or 120 volt AC switch to remotely control the actuators, which can be located meters away from the actual cylinder. So we can have all of these electronic devices located in one power pack, which is conveniently located for maintenance reasons. This is much more what you'll be seeing. These systems here are quite primitive and are used and have their uses, quite frankly, but mostly on power equipment for excavations and things like that. More sophisticated systems will be using electronic controls. Okay. So in this one, this is a breakdown of the system. So the motor itself is just a gear motor. Generally, it's a regular everyday AC motor that is running off the grid, and it is running a gear pump. The gear pumps are quite common in hydraulic systems and are the simplest types of pumps. When we get into pumps, we will be going through the different types of pumps and where they're used and their limitations. The pressure relief valve, as mentioned, is designed to control the system pressure. If the pressure is too high, it can damage the components. So we make sure that we have a maximum pressure relief valve there to keep the pressure inside the unit at a certain level, and any excess pressure will then be vented back to the tank so the fluid can settle down. But again, this isn't something you want to be going off all the time. So your maximum pressure relief valve is going to determine what your ultimate system pressure will be, but not necessarily the pressure at which it operates at. Any hydraulic system will only work as hard as it needs to. If this load is 2,000 kilograms, the motor will be working harder than if this load was 1,000 kilograms, regardless of the amount of fluid that will be going through it. The speed at which the fluid could be traveling could be exactly the same. However, because the load is lighter, the force on the motor and the system is therefore less. Okay, applications for hydraulics. Hydraulics are very useful for generating large forces. Tons and tons of force. Hydraulic systems are used for brakes. They're also used for automated material handling, such as in mines and manufacturing. I worked at a mine that had 7 kilometers worth of hydraulically actuated motors that drove the conveyor belts to bring the ore back to the mine. Huge equipment. Pitch rams for compacting garbage, also pitch rams in hydraulic systems of wind turbines. We'll be using hydraulic systems as well. Anywhere where you need a large amount of force. Another place you can use hydraulic systems is to multiply force by using the length of the moment arm as well as the different sizes of the cylinders to create a force multiplication. So if you're ever wondering how you can push with 10 kilograms of force on your brake pedal and it stops a 2,000 kilogram car, if you were pushing on the side of the tire, there's no way you would be able to control that much force to stop the car. But by using hydraulics, we can use these multiplication factors to make the system much more efficient, and you get a lot of output for very little input. Okay, so here we have the first basic triangle. Force is equal to area over pressure. So if I'm looking at this particular system right now, here's a small piston in the master cylinder. The small piston in the master cylinder is acted upon by your foot, which pushes on a long rod. That rod multiplies the force by using the length of the moment arm and the very small master cylinder. And on the other side of the master cylinder, you have a very large diaphragm. That large diaphragm increases the area and therefore increases the pressure, because the pressure is the force over the area. So if we made the area larger, we make the force larger, regardless of the pressure. So that's one of the key things to remember, is we can definitely move that. Now, if I take a look at this diagram here, you can actually see it working. As the operator of the vehicle pushes down on the brake pedal, number one, the moment arm from this pivot point here is generally on your brake lever. You'll notice it's about a ½ meter long. They can be fairly long. That's pushing on a very small cylinder. The cylinder doesn't have much area, but since it's sealed on both sides, that means that the pressure that's built up cannot escape. And due to Pascal's law, it will act upon all of the surfaces at a 90-degree angle. Now you can see that the diameter here is much smaller than the diameter on the other side of the caliper. As a result of that, it provides much more force multiplication, and that allows, again, when I move it down through these small capillary tubes, an extremely large output force on the car's brakes. So the brake pads can have thousands of Newton meters of force on them, even though there was only a few Newton meters of force that were really a try. Okay, so a closed system necessarily need a pump. Well, a closed system is like Pascal's law, and all of the fluid acting upon that will be acting at a 90-degree angle with the same amount of force. Right? What type of applications use hydraulics? Pretty much everything in industry where you need a large amount of force in a small, compact, and easy to set up system. The disadvantages of hydraulic systems, well, they are expensive, the fluids can be hazardous, and you can have messy leaks, and some of the fluids actually are a fire hazard as well. Plus, you can have cross-contamination of fluid into some things like plastics or food, which would not react very well to hydraulic oil, as you can imagine. But that's more than made up for by the advantages of the hydraulic system, which has infinitely variable speed control. The more or less fluid that I meter through that restriction will affect the speed, but not the pressure. I can also determine the amount of force that I move through it by changing the size of the conductors. So it has a highly accurate control of movement and can be used in robotics to set a welding rod on a car, application after application, car after car, with the precision of down to 100ths of an inch. So hydraulic systems, as we'll learn in the next coming lessons, are extremely useful, and you will be working with them in industry quite a bit. I'd like to thank you for your time, and don't forget to tune into the next 2 videos that will take you a little further down the introduction, and also remember to do the questions at the end.